this rapid session, we are already advancing to the next part, the hardware panel, with Kristen Pudenz from Atom Computing, Bharath Kannan from Atlantic Quantum, and Nick Bronn from IBM. We are preparing the spotlights, and here we go. Extremely happy to have this panel together. Kristen Pudenz is the Director of Advanced Research Programs at Atom Computing, neutral atom quantum computing focused company. Nick Bronn is a quantum researcher at IBM, focused on superconducting qubits. And Bharath Kannan is the CEO of Atlantic Quantum, also focused on superconducting qubits, but in a different way and at a startup. Would you like to give a bit broader introduction to yourself and to the company, starting with Kristen?
Thanks, Marlu. So I'm Kristen Pudenz. I work on research programs at Atom Computing. That really means that anything we do with anyone outside the company to accomplish shared scientific goals, that's my purview, and it's what I'm interested in doing. So I think there's a lot of talent here in the room today, and hopefully in the future we'll work with some of you to realize quantum applications and advanced research on our platform. Before I was doing this job, I was corporate lead for quantum at Lockheed Martin. So I was responsible for computing, communications, and sensing across the corporation as a whole, which is a diverse and varied role that I enjoy quite a bit. Before I did that, I was a quantum applications engineer working for Lockheed Martin, implementing different problems that were of interest to the company. And before that, I did applications and error correction on the first quantum processors ever released outside their lab of origin at the University of Southern California. So I'm excited to be here today and talk about the world of quantum computing hardware.
Very excited too. Thank you. Could you share more about yourself and about the company too, Bharath?
Oh, about the company too. Sure.
Go ahead,
Yeah.
Kristen. Yes.
Okay. Sorry, I missed your prompt a bit. So about the company, Atom Computing is building neutral atom quantum hardware. So that's we say neutral atoms to distinguish it from the ubiquitous ion traps. So we use strontium and ytterbium atoms. We trap them in laser tweezers, and we have a whole plane of them in a square lattice, and we do actuate single qubit gates with a laser transition, and then we excite to the Rydberg states in order to realize 2 qubit gates between neighboring atoms. This technology is extremely scalable. We think we can generate more traps for atoms by generating more spots of light from our laser systems, and we are always trying to generate many clean and useful laser spots to do trapping, to do gates, to do everything that we need for the quantum computation platform. So right now, we have a 100 qubit prototype in the lab in Berkeley. We're building substantially larger commercial systems, and we see a rapid scaling curve for the number of atoms we will have in our traps, looking toward the future, both scaling in 2D and moving to 3D systems a couple of generations down the line. So it's a really exciting time to be in neutral atom quantum computing hardware, and I look forward to telling you more about its development.
Really exciting. Thank you. Let's hear more about Atlantic Quantum 2, Bharath.
Yeah, thanks. I guess one thing is I'm actually calling in from the airport, so if you can hear any background sound, I apologize for that. Hopefully it's not too bad. But yeah, so I'm Bharath. I'm a co-founder and CEO of Atlantic Quantum. And as was mentioned previously, we work on superconducting qubits, a different flavor than what is most people use today. Kind of, I think Nick will talk more about that. We use a qubit called fluxonium. It's actually been in the academic sphere for quite some time, but people really haven't been taking it too seriously until I think the last couple of years. And we've done some really exciting work at MIT, which is where I did my PhD prior to starting Atlantic. So I was at MIT for 6 years. Previously did my undergrad at Rutgers in physics, after which I graduated and moved up to Cambridge. And when I finished the PhD, a bunch of us in the lab were really thinking about what to do next. and this idea of kind of taking our research that we thought was really promising and offered a different flavor of superconducting quantum computing to the field was very exciting. So that was definitely a big reason as to why we started that. Yeah, and I can talk a little bit more about the details maybe later on in the panel.
That sounds great. Thanks, Bharath. And we have Nick Bronn, a quantum researcher at IBM.
Yeah, hey everyone, it's a pleasure to be here and talking to you all and with my fellow panelists today. So I was trained as an experimental physicist, and I joined IBM first as a postdoc and then as a research staff member working on building the quantum hardware that we started with. I guess we started with like about 3 qubits when I was there, and the qubits we use are the well-known transmon, where we store the quantum information in the oscillations in tiny superconducting circuits, which are going to be different from what Bharath is going to tell us about. So I was building the hardware and kind of scaling up to the tens of qubits and hundreds of qubits we have today. But then after 6 years, I moved to the deployment team. So I was training people and doing the experiments they used to calibrate the qubits. So you're talking about, instead of like laser beams, you're talking about microwave pulses in that situation. Putting up quantum computers in different countries, like in Germany and Japan. I trained those teams to deploy those systems during the pandemic, which was an interesting experience. And then after that, I kind of moved to the software side of things, where I'm more outward facing, and I use our open source software development kit called Qiskit to enable researchers, especially external researchers, to use our backends that we have online and are available. Some of them, many of them are available for free. You just need to sign up. I make them useful as research tools for mostly academics, workers at national labs and such. So I've been doing that for about 3 years, and so I kind of work in enabling people. I work in like education, making YouTube videos, and I end up collaborating with a lot of these external parties as well. IBM, if you don't know, we've been a company that was kind of involved in classical computing, and one of the reasons we use superconducting qubits is because you can fabricate them using the same, more or less the same techniques that were available for CMOS architecture and stuff like that. So that's why IBM has a history in superconducting qubits, and it goes far back as to the 80s, when people wanted to build classical computers out of superconducting circuits as well. So that's kind of where we come from.
Great. Brief question to Masako, who just gave the talk. If you are online longer, feel free to turn on your video, and we will include you in the panel to shine your light on trapped ion technology as well. The panel will go as follows. Yes, then if so, please turn on your video. The panel will go as follows. We will discuss for 5-10 minutes about different qubit modalities. What will be the best quantum computer? Who will achieve quantum advantage earliest? What is best scalable? And then field questions from participants. And there are actually already quite some coming, especially which hardware is application ready already. And I know that all of you are working on applications as well. We have the distinction here at the moment, neutral atom versus superconducting circuits. Would you like to shine your light, Kristen? What do you think are really the big advantages of the neutral atom technology, but also the disadvantages? Where might superconducting technology be better?
Sure. Well, I think the primary advantage of superconducting at this point is that it exists and it's on the cloud already, right? I think people can go to IBM's website right now and go take a look and get access to some of their smaller systems. And that's great. And we need quantum computers, and we need people developing applications for them. Neutral atoms is a more recent qubit technology than superconducting systems, right? People have been thinking about neutral atoms in the context of quantum information science for quite some time. The earlier applications of neutral atoms were in areas like clocks and inertial sensors, and those are still active areas of technical development for the technology. But atom computing was founded in 2018, and that's kind of when that's the same time as the development curve really took off for neutral atom quantum computing technology. So we think that we are scalable and we are quick, and that our qubits are very clean. And those are some advantages of using neutral atoms. We have extremely long coherence times with neutral atoms, particularly the neutral atoms that we use at atom computing. So we use nuclear spin qubits. You can, when you're using an atom as your qubit, you have a sort of a choices on the menu in front of you. You can pick any two levels within the electronic structure of the atom and use those to realize your qubit. At atom computing, we use the nuclear spin, and we've been using it for a prototype. We're using it for a commercial system, although we are changing the alkaline earth-like atom we use from strontium in the prototype to ytterbium in the commercial grade systems that we're currently producing in Boulder. Those nuclear spins are quite well protected because by the atomic structure of the atom that we're using. And so we get coherence times in the tens of seconds. This is really remarkable for commercializable quantum hardware, and we're proud of that achievement. It gives us space for deep circuits, although of course you need strong gates for that as well. And it also gives us space for error correction, right? And I think a lot about error correction because I think about the potential for scaling this technology far and for making it useful in the long term. We need serious error correction to do that. And when you have a long coherence time, you have time to fix some of your qubits and let the other qubits wait for you to catch up. And that's a real strength of neutral atom technology. The other thing that's nice is most qubits live in specialized containers of limited size. You can put so many ions in a trap, so many superconducting qubits in a trap before you run out of space in your ion trap or dilution fridge. Neutral atoms also live in a specialized container of limited size, and that would be our vacuum cell. But we've been probing the limits of scaling within the vacuum cell, and we think we can put single-digit millions of qubits into a single module before we will have to start developing interconnects. And that's really exciting. That's an interesting development curve that we think will achieve us to allow us to race to early fault tolerance very rapidly.
And Nick, I see some comments. IBM has already claimed quantum advantage, right? I think this refers to the quantum utility with simulating the Ising model. Can you share about the superconducting advantages, status, challenges?
Right. So, I mean, I guess I can start with talking about when you're talking about claiming quantum advantage, you're looking at comparing the best classical models that you can possibly make to whatever you can do, quantum mechanically. And what we're able to do is take a relatively simple Hamiltonian on a very large system and compare it to the best kind of tensor network methods that we could come up with. And others are free to come up with, and they have, and try to compare them to what you can actually do with a quantum computer. So this is like, kind of the problem that maps best to our system, in that it's a, lattice of spins that reflect the topology of our hardware. So it's not really kind of a general purpose thing, and I don't think anyone wants to claim that, but you kind of want to be able to take your best machine learning techniques and compare them to what you can do with available quantum computers. So in that way, it's kind of impressive.
And where do you see the challenges, scalability, difficulties for superconducting quantum computing? Will superconducting quantum computing win the race?
I mean, it's too early to tell, I think. There's a lot of effort that needs to be made, a lot of development that needs to happen. And, even with superconducting quantum computers, we do change, our architecture, here and there with, the modularness and the kind of coupling we have between our qubits and stuff like that. So I think it's, something that's going to evolve. I think superconducting qubits have a strong claim to see a path to scalability. So that's something I'm positive about.
Amazing. Then Bharath, Atlantic Quantum is pretty new, really exciting startup, but in a busy field with big giants like IBM, Google, Amazon coming. What is your selling point? How are you going to beat Nick?
Well, Nick and I will grab some beers when that happens for sure. But
Federation is best, right?
I think to that's right. I think maybe taking a step back, it's a very like obvious question to ask, why yours versus somebody else, and there's clear answers for disadvantages and advantages that have been outlined by both Kristen and Nick. But I think the one thing that often gets kind of left behind is this is a very nascent field, right? And if there was a clear answer, right, maybe one of us, maybe none of us, maybe multiple of us would already be able to make that claim, right? And there's a lot of it's just unclear whether, is it going to be 0? Is it going to be 1? Is it going to be 2? And we're all just working really hard to pushing our respective fields forward. And often you see you can ask the question why you're working on the specific modality you are. And to be frank, the answer is generally I work on this because it's what I've been working on, right? This is the thing that I've been doing to push the field forward. You very rarely see kind of, people who have deep expertise in neutral atoms going to superconducting and vice versa. There's a few exceptions, right? But the point is that there's just so much to learn that we need to learn in each of our respective hardware platforms that you need this kind of like, deep expertise in each individual platform to know how to push it forward. So that's the one thing I would want to highlight is there's a lot to learn. And that's why having these big players in the field.
And I think you were already successful because it seems that Nick fled right away. So he actually arranged his substitute to defend himself better. Olivia Lane. So I'm adding you to the panel. Wow, take it further, Bharath.
We all love Nick. We don't want Nick to run away.
Yeah. What kind of qubits will you make a change?
Yeah. So as Nick mentioned, we work very similar to kind of the type of stuff he's working on. These circuits made out of superconductors. But much like the way I like to think about it is, much like you have the constituent elements of actual atoms, right? Protons, neutrons, electrons. There's an analog for that for our circuits, right? So we have inductors, capacitors, and these things called Josephson junctions. And the way in which you arrange them can create a different type of artificial atom in some sense, right? So just like you have a periodic table of real elements, you could say there's a periodic table of artificial elements. And the transmon is certainly the one that has gotten the most attention and the most time spent in both academia and in industry. But the type of circuit that we're working on, Fluxonium, is a slight twist on that. So the transmon, I would say, is the simplest superconducting circuit that one can make to act as a qubit. And that simplicity, is great because it allows you to kind of take that circuit and start to scale it up to the few to tens to now even the hundreds of qubits. Fluxonium, on the other hand, is a slightly more complicated circuit. There's an additional circuit element, this inductor that you have to add to it, but that added complexity we think gives you advantages on some other side. So, for example, we recently put out a result showing what I think is, at least currently in terms of published results, the world record for averaged 2-qubit gate fidelity, albeit on a small prototype system. So there's still questions about how this thing scales as you increase the number of qubits. Can you maintain that fidelity? But nonetheless, a very interesting result. And it goes to show that you actually can use Fluxonium qubits to get this high level of performance. It's no longer, I think up until that result, you could have claimed that Fluxonium was at best equal to what transmons could do. But I think this is really the first result that we've shown that can show there's indications of perhaps going beyond that. And kind of one more comment that I would make is this notion of scalability. I think it's actually, people use the word too much to the point that it's almost lost its meaning. When someone tells me their system is scalable, or when I tell someone my system is scalable, I feel like people don't even know what you're talking about anymore. And the way that we really think about it at Atlantic is we fundamentally believe, at least as things currently stand, it's error correction or bust. We think that the true value of quantum computing as far as things that we know will work for sure, really only occur at the point of error correction. And so the question is, what does your hardware require to reach that scale, right? And that's going to differ based on if you're using neutral atoms, ions, superconducting, connectivity is going to be different, right? Your gates are going to be different. So you have to take all of these things into consideration. But I guess keeping it to superconducting qubits, we're likely going to require, tens, hundreds of thousands, possibly even millions of these physical qubits to get to the true value of fault tolerant quantum computing. And so you can almost take an inverse approach of setting your engineering boundary conditions of what is fundamentally required to build a million qubit processor, right? How am I going to do this? What are the boundary conditions, the constraints that I need to make sure that I follow as I'm building up, right? Because no one's going to go from 0 to a million in one day. That'd be great. I'd love to do it, but I can't. And I don't think anyone else has that capability. If not, then, I guess we'd have a quantum computer tomorrow. But you still have to go through that, that 0, 10, 100, etc. But you have to make sure that the things that you're doing at those smaller scales are compatible with the constraints of getting to error correction, right? And if you're not doing that, if you do something that works at 100 or works at 1,000, but doesn't really work beyond that, are you really going to be able to extract the value? And so that's really our mindset.
Yeah, extremely important. And we have Olivia Lanes joining from IBM. People are commenting on the Discord. IBM is bringing big guns after the points by Kristen and Bharath being made. Olivia, the North America quantum lead of IBM, quantum researcher and IBM Qiskit community leader. Can you share more? How is IBM going to do this? What is the roadmap and ambition of IBM? Will this be with transmon qubits? Will you also go to different types of qubits? We'd love to hear the ambitions and vision.
Yeah, sure. So sorry, first of all, I guess, for replacing Nick. Nick had an emergency, but I'm happy to take his place. Nick and I have a similar hardware background and are now doing software and community work. But yes, to answer your question, IBM is very committed to the transmon qubit model for scaling its systems. I don't have it up right now, but you can Google the IBM quantum roadmap and see our plan for when we plan to release every single processor for the next, I think it's 7 years, if I'm not mistaken. And so last year we released the Osprey processor, which is 433 transmon qubits. And then this year we plan to release Condor, which will be the first 1,000+ qubit system, which is very exciting. But as we plan to scale our processors, we're also going to be integrating what we're calling interconnects. So we realized, fairly early on in the journey that it didn't really make sense to continue to make just monstrous processors in terms of the size, because although we're getting very good at making reproducible transmons and architectures, it's going to be necessary to have a bigger chip than would fit inside a reasonably sized cryogenic system. So these interconnects are going to be connecting different processors to one another. And we don't expect those processors to be larger than like probably 1,000 qubits. And then those interconnects will create, different parallel systems that are connecting all of these processors to one another. And that's an incredible engineering challenge that we're working on right now. But that's something that's going to be a huge focus for us in the next 2 to 3 years.
How do you see the competition with spin qubits in silicon? We had a talk about that yesterday. Very long coherence times, fast gates. Is that a contender for the superconducting technology?
I mean, we had some work going on for spin qubits in Europe. All of the hardware research in the US is focused on superconductors, but in Europe, we had a team dedicated to looking at spin qubits. It's a much, much smaller team because we just think that although the technology is getting there, and that's really exciting to see as a scientist and just like as an industry professional, we know that we can leverage in the superconducting industry a lot of the fab and the technology that comes from the semiconductor industry. So we plan to be utilizing that and scaling that up as we continue to make our processors. So I mean, this is all to say I don't know. maybe, one day spin qubits will overcome a lot of the fab challenges that I know that they have are intrinsic to those systems. I don't see that happening in the short term, but 10, 15 years, who knows?
Yeah, I am in the meantime monitoring the Discord, monitoring the Zoom, and already fielded some questions. Kristen, how do you see the bigger field? Would advances in other technologies, let's say lasers or others, significantly advance neutral atom quantum computing? And where do you see the challenges for scaling?
Yeah, so challenges for scaling neutral atoms are really, the number of atoms you can look at it at once with a single microscope objective, the power levels and cleanliness of beam quality that you can achieve with lasers. It's not hard to get atoms, it's not hard to trap atoms, but like generating the traps and executing your gates well, that's something that we're quite interested in doing very well at a very large scale. So, we're very focused on our laser supply chain. We work directly with certain laser suppliers to get us the things that we need. And we're optimistic that scaling curve looks sufficient for what our needs will be, even to very large systems, to these 3D systems of single digit millions of qubits that we're targeting at the far end of our development roadmap. In the near term, what we're really focusing on is getting the noise levels down in lasers as quickly as possible, because that contributes to all the fidelities and the noise in our system. We are definitely laser noise limited at this time, and we intend to work collaboratively with the scientific community to make that, we're already building working systems, but we want to go to higher and higher levels of performance, and we believe that's possible in the near term. Other things that enable our technology, like these microscope objectives, we already have supply lines established for that, and we are working with the scientific community to enable massive parallelization of our gates, massive operations over our qubit array, so that we don't need to wait for serial operations. We can do them all at once, and we can execute our circuits efficiently. Just because we have the coherence time available to wait around doesn't mean that that's something that we want to do with our systems.
Could you also share a bit? We had a talk by Quera, Pedro Lopez, on their basically analog mode. We had a talk by Jeff Thompson from Princeton. Could you give an overview what the different approaches within neutral atom quantum computing are, and what atom computing chose to do?
Sure. So these analog approaches are very appealing, and I can see why Quera has done what they've done with their analog system, right? The really nice thing, as I was talking about parallelism of control, right? And if you're going to control a neutral atom system in parallel, what you actually have to do is you have to generate many, many spots of light that actuate your gates, and you have to apply those to some qubits, but not others, and you have to not affect the neighboring qubits. And we're getting very good at this at atom computing, right? And we recently showed a mid-circuit measurement result, for instance, that we did readout, and we hid some qubits from the readout, and we read out only others. And we did this with alternating sites, like a checkerboard arrangement within a small array of qubits, and we got very good results, and we hardly affected the remaining qubits at all. So, but this is a challenging discipline, and this is one of the things that we work on atom computing all the time. One very appealing thing about a neutral analog system, and I think the reason that you see these analog neutral atom systems emerging first, is in an analog system you can utilize global control degrees of freedom, right? So you can set up your system with your neutral atoms, and then you can shine a laser across the whole array and apply the same kind of control to all the qubits at once. This is much easier to realize, much easier to implement. implement. And you can do some very interesting things with these analog systems, particularly some of the phase transition results, some of the magnetic results. These are some of the same things that have been done with same class of problems that have been explored with previous versions of analog quantum computers, like the D-wave quantum annealers, right? And so I think that's great science, and it's exciting that we're able to access it in the near term. But the fundamental problem with analog quantum computers is that despite decades of effort, we still do not have a threshold theorem analog for this class of quantum systems. We do not know how we will error correct a large analog quantum computer. So a small analog quantum computer can do maybe some better NISQI things than gate model quantum computers can do. But we know we can error correct large gate model quantum computers, and we know we will win in the end, and we know we can make these systems work in a fault tolerant manner. And that's what's really going to give us the prizes of quantum computing, you know, your Shor's algorithm, your real true chemical and physics simulation of problems that people care about, like nitrogen fixation, things like that. So I think that's why we drive so hard to that goal, and we stay very focused on the gate model of quantum computation. So I hope I got all your pieces of your question, Marlu. I feel like that was a rich one.
Yeah, extremely exciting and interesting. All three of you also have a really inspiring career path, and I would love to for all of you to share a bit about that, and to share about your decisions. Bharath becoming an entrepreneur, becoming the CEO of Atlantic Quantum, Kristen coming from Lockheed Martin, then joining the startup Atom Computing, Olivia doing both research and the community aspect. Would you like to share a bit of your personal story and also your message to everyone, starting with Bharath?
Yeah, sure. I think for me, like if you asked me even like a year and a half ago if I'd be doing what I'm currently doing, I would have definitely said no. You know, I come from a family of immigrants, right? And you know, I've seen how hard my parents, for example, have worked, you know, to come from India to come here, give me the education to do. And there's really kind of a cultural background to growing up as the child of an immigrant, that, you know, you should have a good education, find a nice stable job, and live a good life. And that's really kind of the mindset that I had for most of my life, to the extent that even when I was at MIT, I actively avoided doing anything that had to do with entrepreneurship. You know, there's lots of opportunities at MIT that I unfortunately didn't take advantage of when I was there, to, you know, get yourself into learning about how to start a company and what does the world look like from that angle. And I took a very conscious decision to not think about those things, because I just didn't want to do a startup, and yet here I am. So, you know, the real turning point for me was, you know, at the end of the PhD, a combination of two things. I think one is, you know, you're generally not, most people do not have the opportunity to do something like this, right? And by opportunity, I mean both in terms of, you know, the technology that you're developing, you know, in your research, whatever, but also in terms of the people that surround you. And the team that we kind of, you know, came together with to start this company, I just didn't see having that kind of an opportunity ever in my life, except for that moment. And that was really the most important thing for me was that team. So I clearly remember the phone call I had with my parents when I told them that I was going to do this instead of taking a job at a very, you know, stable position with good pay and whatever. And it took them a few weeks to understand that this was an exciting opportunity, but, you know, when they did, they also fully backed me, and that totally sealed the deal.
What is the main lesson what is the main lesson you learned, Bharath, switching from this academic environment and not into a big stable company? The insight.
I think it's just to be brutally honest, it's like anxiety management. So being able to know that not knowing everything is okay. Because when you're in academia, you are very sheltered, right? And in the PhD, you have a lot of time. It doesn't feel like it most of the time, but you do have time. And if things aren't working, you can really, take the time you need to figure these things out. And kind of coming out of that, from probably what is one of the most sheltered environments to what is one of the least sheltered environments, it was a very big shift. And I think another important thing was just learning to talk about what you're doing to people who have never even heard of anything, right? It's a skill that you need in I think any job, but definitely as a founder of a company, it's something that you deal with every single day. So, you really, as an academic, you want to get like into the details and the weeds about everything, and that's what excites you. You spent so much of your life working on this stuff, but not everyone needs to understand every single detail. So tempering your excitement,
especially not in a
skill.
startup. Thank you for sharing this wonderful, inspiring story, Bharath. Then there are special requests. Olivia, Varda from India wants to hear your personal story.
Well, I always tell people I'm a failed astronomer. I wanted to be Carl Sagan basically growing up, because I grew up watching Cosmos DVDs. But then my senior year of college, when I was like already applying to graduate school, I did a trip. I did an observing trip with one of my professors, and I really did not enjoy it. I thought it was like pretty boring. But I was finishing my degree in physics. I knew I had to do something with it, right? So I kind of had an existential moment where I was like, what else is available? Like, I have to find something else to do with this degree.
Then you do something where observing really plays a critical role.
And I discovered quantum computing really just by accident, just by like Googling different universities that I might be interested in and seeing what professors they had on board and what kind of research they did. And I ended up going to the University of Pittsburgh. I was just randomly looking at their website one day. I saw they had some professors who did quantum stuff. I had previously worked in a laser lab for a different internship. I thought maybe it could be fun. But I knew I didn't want to do astronomy anymore. So I just sort of blindly sent out some applications, got accepted, thank God. And I went to Pitt to build a quantum computing lab, basically from scratch. So I did that. And then I guess my journey into IBM was also kind of a funny one, because I had two teams that were simultaneously reaching out to me at the same time, which was the education and the community team at IBM, but then also a hardware research team. And I was a scared, insecure graduate student. And I thought for some reason, if I told one team that I would prefer to be on the other team, they would get offended and not give me either job. That makes no sense in hindsight, but I don't know, that was in the mindset that I was in at the time. And so I sort of just asked IBM, well, can I do both jobs? And they were like, well, that's weird, but okay, I guess. So I sort of just negotiated the job that I wanted. And, you can take whatever lesson from that you want, I guess. But I guess the way that I sort of interpreted it is, people will try to put you into boxes and they'll try to tell you, what you are and what you should be and where you should go, because that's easy. But you can just reject that. If somebody says, you're, a hardware researcher, you shouldn't be working on software, why? I can do both. You can always carve your own career. If there isn't a position that you want at a company, you make it, you be the first one, and you just argue why it needs to exist and why you're the right person for it. And if you get people to support you and buy into it, you can do whatever you want.
Amazing. That is really amazing to hear. And it is also the message or story of WOMANIUM. We say, don't confine yourself to only one thing. Explore everything and do everything if you can. And then the most promising things will come out actually at the interface. Thank you for sharing that. This is amazing. And we also have people in the program who are actually in astrophysics and are now exploring quantum computing. So
yeah, this wasn't to disparage astrophysics, by the way. Some of my best friends are astrophysicists. It just wasn't for me.
Right, and this is also very important. Everyone needs to be willing to pivot if that is the better way for you.
Yes, I think that's the perfect way to sum it up. If you're doing something and you find yourself not liking it, just, have the courage to change.
Wonderful. Thank you so much. And Kristen, it's getting dark there. People are saying, oh, the neutral atoms need some more more fluorescence. Can you share more? You were at Lockheed Martin for a long time, then joining atom computing. What is your story?
Yeah, so apologies for the unfavorable lighting. This hotel room only offers me so many options. So, but yeah, I went for my PhD after I'd done a couple of internships in undergrad and kind of seen how the tech world works. And I thought, I want a valuable degree, and I want to make it so that I will always be doing interesting work. And what I had observed was that nobody really sends a PhD to do the grunt work projects. Everybody thinks that the PhD is valuable and you should do something interesting with that. So that's how I decided to do a PhD. And how I decided to do it in quantum computing was that I was looking for one of the really leading edge fields at the time, and I thought I found it there. But the wrinkle was that I'm an electrical engineer, and at the time I was doing my PhD, most people working on quantum computers were physicists, and very few of them were ready to escape the lab. Everybody was making a qubit somewhere in the basement of a science building, and saying that there's a motivation slide that someday this could be used to make a quantum computer. So I came up through a physics group doing my PhD in electrical engineering, and I had the great good fortune that when I was looking for my dissertation project about 2 years into my PhD, Lockheed Martin bought the first commercial quantum processor that was ever installed outside its lab of origin. That was a D-Wave device, and they put it at the University of Southern California, where I was studying. So I did my PhD on that processor. I did the first error correcting code that was implemented from the user side on the commercial processor. And it was a lot of fun. It was fascinating and interesting. And most of all, it was a way to make something that was a really advanced scientific technology useful. And I found that's sort of been the guiding light of my career since. That's something that I'm really motivated to do, and I will do in pretty much any way that I can. So I moved over to Lockheed Martin when I graduated, because they said, okay, come program our side of the processor if you'd like to. And I thought I would like to. So I was the first person I know who had the job title quantum applications engineer. Now we have many, many quantum applications engineers, and it's still just as good a job now as it was then. And I did quantum applications for D-Wave chips for several years before, moving up a level to Lockheed Martin's corporate office, is where I got responsibility for not only computing and not only D-Wave, but the whole portfolio of quantum computers at Lockheed Martin, and computing, sensing, and communications. So that was another opportunity to do interesting work and an opportunity to learn, right? I learned a ton about sensors, learned a ton about communications, both the good and the bad and the ugly, and what we can hope for, practically in the near term, and the medium term, and the long term. That's kind of what the company always wanted to know. And we built a strong grassroots community of quantum practitioners at Lockheed Martin that could support that for the company's goals. I left that position, even though I loved it, because I was ready to do something different. I had spent a lot of time at a large company doing work across the whole gamut of it, but I was ready to do something at a smaller company in a different environment, an environment where maybe we could move faster, where there was a little more risk taking, and where we were working directly on an exciting new hardware technology. And that's atom computing. And I've been very happy to have made the move. I think it's important to have diversity in your career path and the kinds of roles that you do. And again, I'm learning, right? A whole deep dive into neutral atom quantum computers, because I was never an atomic physicist, but now I feel like I'm maybe a quarter of the way there, right? And I get to work with fascinating people every day who are brilliant, and it's the time of my life.
Amazing. I'm going to ask a last question, and with maximum 40 seconds time, I will cut it off. Why is now the time for quantum and now the time for quantum startups? And isn't it supposed to be a quantum winter right now? Bharath, 40 seconds.
Well, I mean, quantum is a very interesting thing in that the technology is in a position where it's almost post-academic in terms of the scale that things need to be done, but it is very much pre-commercialization in that we won't have a fault-tolerant quantum computer for quite some time. And so it's in this awkward position, right? Where is it really a business or is it just an R&D effort, right? And I think, if you're going to have this technology mature, we have to be working on it now. Like I said, you're not going to go from 0 to 100,000 or 1 million in a day. Somebody has to fill in that gap. And whether that's an IBM, an Atom, or an Atlantic, we're all working very hard to fill that gap and get to where we want to eventually.
Over to you, Kristen.
I think it's an exciting time and a good time for quantum computing because we actually have the technology and it's available to put into the hands of multiple users and practitioners, and the community that has grown up around this that is very supportive, that is very scientifically adept, and that is lifting all the boats together, I think is our strength, and I think is why we are maybe supposed to be in a quantum winter, but not actually in a quantum winter right now. So I'm looking toward our broad scientific community to make the progress that we're on the doorstep of, and that's very exciting to me.
Wonderful. And concluding words from you, Olivia.
I guess I would say now is the time to get into quantum, because this is for the first time in the history of humans. If you wanted to learn about quantum computing, you didn't have to build a quantum computer yourself, which I can assure you is very hard. So if you want to get started and learn from hands-on stuff, you can do it through the cloud. There are, there's an IBM provider, but there are lots of other providers as well. And you can really get your hands dirty without physically going to a laboratory. And it's just a very exciting time because we're starting to discover, utility. We're starting to discover things that could be applicable to real world. And, not to go on a tirade, but I hope these applications will make everybody's lives better. So it's just a very exciting time. And I think, the government and companies and the world has seen that. And that is why we don't have quantum winter, even though everybody said it was going to happen.
Fantastic. Kristen, Olivia, Bharath, thank you very much. This was a very fun, exciting, insightful panel. We could discuss much longer. I know there are many more questions, many more discussion points, but we have Catalina from Xanadu on as well, ready for the quantum machine learning workshop. So thank you all very much, and we will be in touch.